Welcome back to Ready to Derive. Thus far in our study of limits, we have determined them mostly from graphs and tables. But these methods have their limitations, pardon the pun. What if, for example, the limit of a function was 0.234 repeating, or even an irrational number like pi? These would be very hard to determine from graphs and tables. So the only tried and true way is to determine limits algebraically. But before we do so, we need to learn some laws pertaining to limits when combining functions. This topic can be a little dry, mostly because the laws are somewhat self-evident, but I hope to liven it up using some interesting functions as examples. So without further ado, let's get started. So let's start with a kind of fun example. We have the graphs f and g graph below. F is the green linear graph with a hole in it, and g is what appears to be a sine graph. And let's just find the limit as x goes to 3 of f of x. So 3 is right here, and as x approaches 3 from either side, on the green graph, it appears that y is approaching 6. So the limit equals 6. Now what about for the orange graph, g of x? So now we need to just look at what's happening at x equals 3 on here. It's continuous, so therefore we're pretty confident that the limit of this is 2. So let me pose this question to you. What would the limit as x goes to 3 be of the sum of the two functions? So intuitively, you would think, well, you'd probably just add the two limits. So 6 plus 2 suggests that the limit would be 8. And this inclination is correct, but let's verify it with graphically because it's kind of cool to look at. So here we have the functions f and g and the red function, which is f plus g. And what's pretty neat about this function is you can tell that it's like its parents are the green and orange function. It contains the same oscillation that the sine graph has, the orange graph, yet it's going up in a linear fashion thanks to the green graph. So it sort of bears resemblance to both of its parents. So what is the limit as x goes to 3? Well, as x goes to 3, let's see what's happening on the red graph. So let's see, from the left, we are approaching the same value as from the right. And that value appears to be 8, which kind of confirms our intuitive guess that the limit of the sum of the two functions seems to be equal to the sum of the limits. So that example leads us to our first limit law, which in words says that the limit of a sum of two functions is the sum of the limits, as we intuitively inferred in the example before. Providing, this is very important, this rewriting the sum in this form can only hold true when the actual limits, the individual limits exist. And you might want to pause this video and take some notes down. It's a little dry, but these are kind of important laws that you have to have under your belt. So the next one, not surprisingly, says that the limit of a difference is the difference of the limits. Once again, providing that the limits, the individual limits exist. And again, quite intuitively, the limit of a product of two functions is the product of the limits, providing that those limits exist. And to our next rule is that the limit of a quotient, not surprisingly, is the quotient of the limits, providing the limits exist, and additionally that the limit of g there in the denominator is not equal to 0. So a couple more laws. This one here is a bit long-winded to put into words, but you can get the gist of it, is that the limit of a constant, c is a constant, times a function, is just equal to the constant times the limit of that function. In effect, you are just extracting out, it allows you to extract c, a constant, out from in front of the function. And then this last one, the limit of a function raised to the power n, and perhaps the root of d would just equal the limit of the function, take the limit first, and then raise it to the power of n over d. So let's put the limit laws into action with this practice problem. In number 1, we would use law number 5, which says that the constant, we can just extract that constant and just find the limit as x goes to 2 of the function itself. When x is 2 for f of x, the limit when x is 2 is 3. So that would be 0.5 times 3, which would equal 1.5. In number 2, we use a combination of laws number 4 and 6. And rather than sort of break it down step by step, I'm going to go to the final scenario, which is you just, that's to 0, the limit as x goes to 0 of f of x over the limit as x goes to 0 of g of x, but that would be raised to the half. So I can take that square root out like that. So as x goes to 0, I'm just going to pinpoint here, as x goes to 0 on f of x, that would become 1. And as g, for function g, as x goes to 0, we are looking at a limit of 4. 1 over the square root of 4 would be 1/2. In number 3, we would use law number 3. So the limit of the product of two functions is the product of the limits, the individual limits, providing they exist. So rather than in sort of what you can do moving forward is you don't have to write out these in-between steps. You could literally just go and see what's the limit as x goes to 5 of f. That exists. Yes, it's 1. What's the limit as x goes to 5 of g? That exists, and it's 3. And the answer is 1 times 3, which equals 3. And let's do the same in number 4. So the limit as x goes to 4 of f of x, oh, it looks like that actually doesn't exist. And the limit as x goes to 4 of g of x, which is right here, oh, that's problematic as well, does not exist, is does not exist plus does not exist. You might think that the limit doesn't exist. And here's the caveat, is that you cannot use the limit laws. Remember, I kept saying it repeatedly. You can only use the limit laws if the individual limits exist. So in number 4, because the individual limits do not exist, we cannot use the limit laws. And but don't give up. Don't just assume that the limit doesn't exist. We need to explore a little deeper. So let's take a closer look at this last problem. We know that a definition, one of the definitions of a limit, that a limit exists if the limit from the left and the limit from the right are both equal to a finite value. So let's take a look at this problem by breaking it up into two one-sided limits. So let's look at, I'm just going to write f plus g instead of all the x's to save a bit of time. Let's think about the limit from the left of 4 and for both f and g. Now, luckily with one-sided limits, they often exist, and as they exist, we can actually apply the limit laws. If they exist, we can apply the limit laws to one-sided limits as well. The rules still apply. So if we look at f from the left of 4, so f from the left of a 4 is, we're approaching this y value of 3. So that's 3. And if we look on g from the left of 4, so 4 is here. As we approach from the left, it seems that our y value is approaching 0. And 3 plus 0 equals 3. Now let's check out what happens approaching 4 from the right. If the individual limits exist, then we should be able to apply the limit law. And let's have a look. So on the graph of f, approaching 4 from the right, seems that our y value is approaching 2. Sorry, a little technical difficulties here. So 2. And on g, if we approach 4 from the right, our y value is approaching 1. Well, what do you know? 2 plus 1 equals 3. These two limits are equal from the left and the right. The limits of the sum are equal. So we can safely say that the limit as x approaches 4 of the sum of these two functions is 3. So, moral of the story is, if the limit laws can't be applied, check the left and right hand limits to see if they are equal in order to prove the existence of a limit. And that brings us to the end of this lesson. I hope you found it helpful, and if you did, please do click like and/or subscribe to my YouTube channel, Ready to Derive. Thank you.